Okay, let's look at our first question. So I have to complete the operator code in functor rigid so that it calculates the three residuals of the three cost functions, which is x, y, z coordinates using a given 3 into 3 rotation matrix, and the hint is that R is the rotation matrix with 9 elements, and T contains 3 elements, which is the translation vector. So let's look at our code. So this is the functor rigid structure, and you can look first. Let's look at the comments which are already provided here. So it says rigid registrations least square term. So this is the formula which we need to be using over here. Uh, R is the rotation matrix, T is the translation, A comma B is a pair of matched 3D points. So A is like our original and B is like the target. And then there is X and Y are constants, R and T are variable. Okay, and then what I did is first I extracted the elements of the rotation matrix R. So I broke it down so it's easier to understand. So it's like R00. So I broke it down into like this structure R000102 and so on. So it's easier to understand the structure of the rotation matrix like that. So first, let's RA plus T minus B. Let's remember that formula. So we have our points A0, A1, A2, and B0, B1, B2, and then so first we have is I extracted the elements of rotation matrix R into these variables, and then so it's R into A. So this is since we have 3 points A0, A1, A2, so we have 3 rotation, and for the same we apply rotation to those points, and then RA plus T, and here is the 3 translation, uh, the values of the translation vector, and finally we for calculating the residual we just have to subtract B from it and multiply it with the weight. So what it did was, for now, so like I think it was the red dots which were inverted, or it was the sand. So what it did is now it has calculated the correct rotation and the translation. So now it looks like it's the same shape. Okay, let's look at the second question. So it's complete the operator code in functor orthogonality so that it would calculate the 9 residuals of the orthogonality matrix constraint. Okay, so it's right below it. So let's look at the comments again. The comments are really helpful. It already provides half of the answer. So first one is the orthogonality condition, which is r to the power t into r. So is equal to I. We can So this is basically the formula which we have to apply over here. Uh, so again, I broke my code down into the R11, and so you can easily understand the structure. So this is our R, our rotation matrix R, and so what I did is, so it's R11 into R11 plus R21 into R21. Now you'll see that for some places there's a minus T1. That's because uh, so the columns of our rotation matrix, when they are squared, they are equal to 1. And from there we can derive this, and if we take this one to the other side, it becomes r11 squared plus r21 squared plus r31 squared minus 1 is equal to 0. So that's why for some of the residuals we had to add a minus t to the power 1. So that's pretty simple how we apply this formula. Now let's look at the third question. So it says complete the operator code in functor det so that it can calculate the residual of the determinant of R matrix. So functor det is here. So what I did here is like it's the basic maths formula. So this is how we calculate a determinant. So yeah, I just applied that very same formula which I showed you. And at the end we can see for calculating the residual, I had to subtract t minus t1. Now why? That's because for a rotation matrix to like consider it a proper rotation matrix, this is like one of the conditions. So determinant of R should be plus 1, positive 1. So if we bring it to the other side, it becomes determinant of R minus 1 is equal to 0. So that's why we have this minus t1 over here. And that's how we calculated the residual for the func det. Now, what's the fourth question? Explain the codes in rigid registration that uses Ceres solver. Ceres solver to optimize a rotation matrix. Okay. This is the function which I have to explain. So let's take a look at the comments again. We want to register points 1 to point 0 by a rotation and then a translation. Okay, so first of all, there's nothing odd over here. The inputs are point 0 and point 1. So we have to register points 1 to point 0. That's what it says. And then we have our rotation matrix, our translation matrix, and there's a constraint rotation. We don't have to do that right now. So currently we have if points 0. So here we are just basically comparing the size that the point cloud 1 should be equal. The size of point cloud 1 should be equal to point should be equal to the size of point cloud 0. Otherwise it'll return false and then this function won't work. And then uh, we initialize the variables over here. So 9 elements are of the rotation matrix R in a row major orientation. So these 0 to 8, this is the rotation matrix, and this is the translation vector. Then series over here we are loading up the problem which we have to solve, which is like the bunny image. And then over here we are initializing the like so functor underscore rigids. Over here it's the so these three functions over here. You can see they are using this auto diff cost function. It's a library from this functor rigid. So from Ceres solver. So what it does is it helps us initialize the cost function for. So over here we are initializing it for functor rigid. Over here we can see, and then we have to initialize the cost function for the functor orthogonality which we solved earlier, and another cost function for the functor det. And then we have to add the residual blocks. Now you might say why we need the residual blocks. So the main point of this program is of using Ceres solver is that we are going to we are going to convert it into an optimization problem. So we can find the optimal rotation and translation so that we have like we can match the 2 points, which is like A and B. So residuals represent the difference between the observed data and the model's predictions. So yeah, that's the main point. We just want to make the residual as small as possible. So that's why we use Ceres solver. Okay, that's it for this part, and then we run the solver and we have some options. So first one is like iterations. So let me run it again. So can we let's take a look at this. So here this has 3 iterations. This current method has 3 iterations. And then there's an option to print progress to std out. So like we can look at this table over here. If I set this to false, if I set this to false, then the table is no longer over here. That table has quite some important stuff over there. So I think it's an important function. Let's see, let me take a look again what was there. Like I think there was so there's iteration, so like we have the iteration number, we have the cost, change in the cost function, the gradient, the step. I think this is the trust region and trust region radius, line search iteration time. So just some basic important stuff. Like it helps us get a brief summary of our series solver, of the performance. So we can see that it's converging or if it's taking a wrong step or not. And then finally we just extract the vars, the variables which we had defined earlier. We store it into our rotation and translation matrix. Okay, so the final question is run and compare your results with and without the rotation matrix constraints. So it's all the way down. Rotation constraint. Here it is. So this constraint rotation matrix, currently it's false. So I'll give you a quick look at the output. So I already saved this output. I took a screenshot of this output. It's the one below. So currently it's false. Now if I set it to true, if I set it to true, we can see that the iterations have increased by a lot. So this is what the question meant when it said uh, even though it's more expensive, I need to explain the benefits of enabling the rotation matrix. Okay, so let's look at the output here once again. So I put them together so it's easier to compare. So first thing we can take a look at is the iterations. The number of iterations are way more. So yeah, so when we enable the rotation matrix constraints, the iterations are way more, and also we can see that cost, the initial cost is the same for obvious reasons, but the final cost, it's the final cost when with rotation matrix is more, obviously since the number of iterations is more too. But both of them result in convergence. So why do we need to enable the rotation matrix? So let's take a look at, so training is 0.0467. So we can see the training error is, so uh, let's not uh, rotation matrix with rotation matrix training error. So the training error is higher, a little bit higher, and then we can see the testing error. Uh, the testing error is lower, little bit lower. testing error a little bit lower, and at the end we can see that the train to test gap, it's way smaller. It's almost like half. So what does this mean? Uh, since the training, what's happening is that it's helping to reduce overfitting. That's the main point of enabling rotation, the rotation matrix. So you can see that our training error with the rotation matrix. So it's not taking as much, it's not fitting the overfitting the model like our training data. And then since the test error is a little bit low, it means that it can generalize itself for like predicting unseen values or unseen points. So yeah, that's why we need to why it's better to enable the rotation matrix. That's it. Thank you, 老师，圣诞节快乐。